This application is the Digital Audio Filter Workbench. It's designed to assist music technologists and other interested parties explore the workings of digital audio filters. There are basically four windows. If we pick up a source signal, a simple sine wave, we have a time series graph, which is a source file. We are going to have a filtered version, and for each of these we have a frequency domain analysis. Here you can see the point at which this sine wave operates, which is 220 Hz. That's determined by this little box down here. There are several different types of source signals. There's a multiple sine, which enables you to pick up to 10 harmonics, which gives a picture like that. There's another one which picks up the odd harmonics, which effectively is a method of building a square wave. The more waves we have, it will build up to a square wave. And also, which is very useful for demonstration purposes, is the first and last. And here we have a sine wave with a sine wave superimposed upon it. And here we have the frequency in Hertz, 220 Hz, and this should also be 2200 Hz. By clicking on this harmonics button, you can see what the current harmonics are. This is represented as the filtered version, but as long as you click on this whilst there is no filter in operation, it will show you the source file's harmonics. In addition to sine waves, we've got square waves. We've got a triangle wave. We've got also a sawtooth or ramp or phaser. And we've also got random noise, which can also be filtered. In addition to that, what we've managed to do is to extract from the gm.dls wavetable file, which comes supplied with all Windows computers, the waves which are built in there to support the MIDI activity. So for instance, we can pick up a piano sound here and it'll ask you what bass frequencies you want. So if we click on that, I should do that, and we actually get MIDI note. We can actually play any of the sounds by just clicking on here or here and click on here to play the filtered sound. Right, we're going to go back to the multiple sine wave because it's the easiest way to demonstrate filters. So we're going to go back to 220 Hz and 2200 Hz, and we're going to apply a simple finite impulse response filter. So we can average it based on two samples, which doesn't seem to make any difference. But if we increase the number of samples to say 40, as you can see, the filter here, the frequency here gets filtered out. So this seems to be quite a nice little filter. As you can see, the high frequencies have disappeared. We can do it the other way around. This works just the same way. And here we have just the high pass filter. The high pass filter is really a differential filter, so we don't actually get any advantage by increasing the number of samples we average it over by. In fact, all that it seems to happen is that the amplitude of the filtered signal seems to disappear. Infinite impulse response filters are more effective in the frequency domain than average filters, simple average filters. And a single pole low pass filter or a high pass filter is equivalent to a normal resistor capacitor filter in analog electronics. So what happens is that if we enter low pass frequency in Hertz and say we want to take out, just let everything that's under 300 Hertz through, we get a reasonably effective filter, but it doesn't eliminate all the high frequency sounds, as you can see. What we need to do is add more poles or push it through the filter twice. The high pass version, we say 2000, is a bit more effective, but there's still a little filter there, little sound there. Right, we can also do band pass. So if we enter the frequency in hertz of say 220, and the notch width is going to be 50 hertz either side, we get a reasonable filter. It starts to, it's obviously disappeared there. We can do a band reject at the same frequency. And that actually creates a problem in that we've got overflows, which is the problem with IIR filters, in that they can become inherently unstable. So if we try and do a reject, and we'll try and do 220 and say 10 hertz either side, and it still doesn't like it. It might like it at 2200, 100 either side. What did I put in there? Yeah, it's rejected the 2200 frequency filter. We still get an error here. Right. If we wanted to know what the coefficients were that are used by this particular filter, we could identify them there. Pole 1 and pole 2 there. And as you can see from the harmonics, we've got lots and lots of harmonics here, whereas we should only have 2. To try and overcome some of this, we can develop what they call infinite impulse response filters, which are either Butterworth or Chebyshev. Butterworth has 0 ripple, Chebyshev has between 0 and 29% ripple. Pass frequency in hertz, we'll say, is going to be 2000, and the number of poles we're going to go for is 2, and say 3%, and enter 0 for low pass. We get a filter again, so we need to make a better filter than that. So what we're going to try and do is 2000, 4 poles, 1 and 1. This is the ripple effect that we're putting in, which enables the filter to center itself. Nice clean filter. Try 2200, 4 pole filter, 1 and 0. And again, we've got a filter, but it's not doing very much. If we take that down to 250 hertz, 4 poles, 3 and 0, we do get a decent filter. Problem with all these things is that the filter has to be calculated appropriately to the task in hand, so it needs better algorithms than we've got demonstrated here. Although IIR filters are notoriously unstable, Windows sync filters are very stable. So here we can say, right, we're going to have a low pass frequency of say 300 hertz, and the number of kernel samples is going to be 200. we get a nice clean filter. How this works is that we develop an impulse which is convolved with the source signal here. This is the impulse. That's not a very good example. I'll do another one in a minute. And it's convolved together to actually create the filtered data. Convolution is notoriously inefficient in terms of computing because it increases exponentially with the size of the kernel. If we do a high-pass filter at, say, 2000 Hertz and a number of kernel samples at 500, we get another nice filter here, and this time we can actually see the impulse, which is that. We can also do a band reject, which effectively, because we've only got two frequencies, is equivalent to the high or low pass. So we can say, right, we want between 2000 and 2300 and 500 kernel samples. So we've rejected that. But not completely, because we've still got that there somewhere. So there's still a trace of that harmonic. What we can also do, because we've got the wavetables at our disposal, is we can pick up a piano sound and say pick up a frequency of 130, which sounds like this. And we want to experiment, say what happens if we take out that harmonic? What's that harmonic there? And that's at 362. So we can try our band reject filter. So we can go 250, say, 270, and the number of kernel samples, 500. Started to make an impression. Not very much difference. So now we say 250 and 270. Number of kernel samples, let's go for 2000, take a while. But it eliminates that. You get a different sound. So that basically is the audio filter workbench. What I'm proposing to do is to utilize this and the tools that I've built to explore filters and digital audio further as time goes by. Thank you.